Okay, in this part I'm gonna talk about RMS norm, which as you can see we have a couple of in fact in a couple of places in Mistral we use RMS norm right here and also right down here and within the attention module just right after attention module as well. But what is RMS norm and what it does? So technically RMS norm stands for root mean square layer normalization, and it's kind of a simplified version of the layer norm. Why? Because it kind of reduces computational complexity, and the reason that it reduced that complexity is because instead of using or adjusting the distribution with mean and variance, we simply use root mean square to kind of do a element-wise, I can say, adjustment. So what is the technically difference? What are the differences between RMS norm and layer normalization? So in terms of features, for example, the mean subtraction, layer norm has that, but RMS norm, there is no subtraction. At the same time, there is no variance because we don't need to calculate variance. It is much simpler. We simply use root mean square. And also, as I said, in terms of computation, it is much lower than layer norm. I think it should be something around maybe 30%, which is pretty good. And stability, it's slightly less stable, but we can do a couple of tweaks to make it better, and especially in long and deeper attention and attention network, it works much better. And yeah, so these are the main I can say features of RMS norm. And in terms of advantages, as I said, it is much faster and fewer floating points operation, and as I mentioned, it's much better, it works much better in very deep transformers like Mistral or LLaMA or any of these giant language models. So how it looks in terms of mathematically, so imagine that we have an x or a vector in d-dimensional vector, or we can just simply see it as a embedding in d-dimensional vector space. So for layer normalization, what we do, we technically need to calculate the mean and variance and then subtract each of the elements of that vector from mean and divide them by variance to kind of readjust them, readjust that distribution. But and there are a couple of learned parameters, but here in RMS norm all we do is simply we use this equation which you might have seen in RMS error or something like that. So yeah, as you can see, there is no subtraction and there is no mean calculations. But how it looks like in terms of floating point operations, so imagine that we have a vector size of d, or let's say we have an embedding of within a vector space of dimension 500. So we're going to count how many operations we need to do a layer norm on that, and how many operations we're going to need if we want to do RMS norm. So according to the equation, so we need to calculate the mean, subtraction from the mean, square differences, sum of the squares, divide by d and add epsilon, I don't know, a square root, divide each by standard deviation, and then gamma and beta. So as you can see, we have all these operations, and technically once we do all that, it would be something around 4,000 floating point operations. But on the other side, if we want to do the same thing with RMS norm, as you can see, it simply is, if I can adjust this, yeah, it's simply just a square inputs, sum of the squares and division, and that's it technically. How many operations? 2.5k, which is pretty good, as I said. So it would be something around, let's say, 37.5 fewer operation, which is just massive. It's a lot of operations, fewer than the normalization. And as I mentioned, this is how it looks like in terms of the mathematics behind it. And it's pretty simple. And if you want to just go back to the code where you can find it, where you can find the RMS norm, is technically on the Mistral code. You can just go under transforms layers. And by the way, I will put all these into my GitHub repo together with the PDF so you can have a look at it. And if you want to find more details, and as you can see, so the RMS norm here, it is simply just defining the epsilon, defining the learned parameters, and then what we need to do is simply we need to calculate that square root of the vector. And the reason that we are using torch.rsqrt, it is the reverse of the sqrt. So that's technically, as you can see, this RMS and this sqrt is under this what's that, x is over that, so we need 1 over RMS. So this is exactly what it does, and it makes that 1 over sqrt for us. And then we calculate the mean, and the reason that we have -1 is because we want to do the mean for features, based on the features, which is technically the last dimension here, and we will keep the shape of the tensor as it is without any modification. And finally, on the forward pass, we just passing a tensor, and we do the norm and just simply calculate and multiply that by the weights. And technically that's it for RMS norm. And so technically the next step would be, I think, the attention module, and the group query attention and a sliding window attention.